Hey y'all, so this is actually the second time I'm trying to make this. I just went trick-or-treating with my daughter, so I came back up here afterwards so that way y'all would have this video, so sorry for it being late. I know I promised a couple of y'all I would have it before I left school. So, at any rate, what we were doing, hopefully you picked up this paper yesterday. This is 3-4, zeros of polynomial functions. The essential question is, how do I use the rational zero theorem to solve polynomial functions? Again, we're trying to do the majority of this without a calculator. So, trying to use the properties, and even if I do let you use a calculator, I'm going to want you to be able to verify the theorems and whatnot. There are a couple functions with the graphing calculator that does not work. It's better. Okay, so each one of these, the question is, when finding zeros of polynomial functions, what kinds of numbers can we get? So if we look at this, each one of these is called a factor. And we solve factors by setting them equal to 0. So each of these is called a factor. Factors of the polynomial. Okay, we solve each of these by setting it equal to 0. So remember, we say x plus 3 equals 0. So my 0 equals, so that means x equals negative 3. It equals 1/2. It equals negative square root of 2. It equals positive square root of 2. So it gets a little bit dicey, so I'm going to put it over here. When I set that equal to 0, I see that x equals 4 minus 5i in that case. And then on this one, I see that x equals 4 plus 5i. Okay. There are different types of zeros. There's rational zeros, irrational zeros, complex, imaginary, and then there's also, those are separated between real and non-real. So if we look at these two types of zeros, these are both rational. Okay, which means that they either have a repeating decimal, they can be written as a fraction, that these are going to be irrational. It can't be written as a fraction, and they have non-repeating decimals. And then these last two are complex or imaginary. And even these can be separated into two categories. So these two things are real roots. They occur on the number line. So these are where the polynomial will cross the x-axis specifically. And this is called a non-real. Okay, so a lot of today wraps around this rational zero theorem. So if f of x is some polynomial that has integer coefficients, and p divided by q is a rational zero of f, so like these two, then p is a factor of the constant term, a0, and q is a factor of the leading coefficient term, a sub n. Okay? So we're going to look at a polynomial and look at its leading coefficient and look at its constant last term. Okay? And so the possible rational zeros will be the factors of the constant term divided by the factors of the leading coefficient. Okay? So let's list the factors. And what factors are, let's put this off to the side. Factors are just numbers that multiply to give a number. So for instance, the factors of 6 are going to be positive and negative 1, positive and negative 2, positive and negative 3, and positive and negative 6. So I could pick any two out of those two out of that set and multiply to get that number 6. Okay. So here my leading coefficient is negative 1. So my factors are going to be positive and negative 1, because the ways that I could get 1 are going to be 2 positive ones. Actually, I could get a positive, and a negative, or a positive and a negative, a negative and a negative and a negative. Okay. 4 is going to be plus or minus 1, plus or minus 2, and plus or minus 4. Okay, so the possible zeros, we're going to take these, and they're going to go on top, and then this one's going to go on the bottom. So the possible zeros I'm going to take any combination of these. Okay, so if I take positive negative 1, I divide it by a positive negative 1, I'll still get a positive negative 1. If I take 2, positive negative 2 divided by positive negative 1, I get positive negative 2. And if I take this and divide it by that, I still get positive negative 4. Okay, so the possible zeros possible real zeros, the word there, real, or real rational zeros, are going to be positive negative 1, positive negative 2, positive negative 4. Okay? This is going to be useful in finding numbers that divide a polynomial, so that way we can get it into the point of factoring. So now we're going to list all possible rational zeros of a specific function that has a little bit more to it. So this one is 15x cubed plus 14x squared minus x minus 2. So 15 has quite a few factors, right? It's got positive negative 1, positive negative 3, positive negative 5, and positive negative 15. Okay, then we have negative 2, which is positive negative 1, positive negative 2. Okay, so the possible factors are going to be combinations of these numbers. So you're going to make a fraction. So you'll have positive negative 1, positive negative 3, positive negative 5, positive negative 15. And then we have positive negative 1, positive negative 2. Okay, well, the 1 doesn't change anything. So my possible zeros, so rational zeros, are positive negative 1, positive negative 3, positive negative 5, positive negative 15. We got 4 of them. I take in turns where. Then we have positive negative 1/2, positive negative 3/2, positive negative 5/2, and then positive negative 15/2. Now this is where we're actually going to get into it, where it specifically says, and this is our essential question, how do I use the rational root theorem to solve polynomial functions, and also using everything we know about quadratics with it. Okay, so we're going to find all zeros. So my leading coefficient right here is 1, so this is going to be positive negative 1, and this one is 6, so I have positive negative 1, positive negative 2, positive negative 3, positive 6. Okay, so if I divide these by that, my possible zeros are positive negative 1, positive negative 2, positive negative 3, and then positive negative 6. So first we're going to try 1. Remember, we put the 0 here. This means that x minus 1 is a factor. And I'm going to write my coefficients for my synthetic division. This comes down 1, 1, 3. 3 times 1 is 3. This is negative 2 times 1 is negative 2, and I get negative 8. So that means that x minus 1 is not a factor. Let's try negative 1. Same numbers across. 1. That'll be negative 1. 2 plus negative 1 is 1. Negative 1, negative 6, positive 6. Uh-oh. That means that x plus 1 is a factor. Then, what we're going to do is we're going to take the polynomial that I got when I divided x plus 1 by that. So now my f of x equals, in parentheses, x plus 1, and then we have x squared plus x minus 6. Well, from what we know about quadratics, we know we can factor that. So f of x equals x plus 1, and this will be x plus 3 and negative 2, right? So then my zeros, all of my zeros are going to be negative 1, negative 3, and then 2. You can always verify this and check. Remember, zeros are where they cross the x-axis, so if I graph this, x cubed plus 2x squared minus 5x minus 6, sure enough, it crosses at negative 3, negative 1, and 2. Okay? So when it asks me to solve, it's asking for my zeros, which can be real, they can be non-real, they can be rational, they can be non-rational. Okay, so moving on, let's practice it some more. And actually, this one gives me a huge blank space, so that way I can mess with it. Sorry, my nose is like a faucet right now. I don't understand. So this is positive negative 1. And the factors of this are positive negative 1, positive negative 3. So in this, my possible zeros are going to be 3, they're going to be 1, negative 1, 3, or negative 3, right? Because I take these and I divide them by that, which does not change anything. So just to show you this is plus or minus 3, plus or minus 1 divided by plus or minus 1, and that gives me all 4 of these. So we'll put our 0 in here, and we're going to test it. This comes down, 8, 19, and 16. X minus 1, not a factor. We got negative 1, 1, 7, 11, negative 3, negative 1, 6, 5, 16, negative 16, negative 19. X plus 1, not a factor. And we're super fast at this. We can just keep rolling through. 1, 7, 11, negative 3. 10, 13, 24. Just kidding, 30. That should be 30. And this is 41, right? 41 times 3 is 123. So this would be 120. Okay? And then we have negative 3. 1, 7, 11, negative 3. Now we know that it needs to at least have a single root, especially since this is a cubic function. I know that it's either going to be odd, and based off the symmetry, it has to at least cross once. Sometimes it can cross 3 times, but it's at least going to cross once across that x-axis. So 1, negative 3, this gives me 4, negative 12, negative 1, and then positive 3. And hey, lucky charm, the last one is, that means x plus 3 is a factor. So now my f of x equals x plus 3, and we're left with x squared minus 4x plus 1. Okay? Now this is not factorable. So we're going to solve this by the quadratic formula. Or you can complete the square. I don't care, whichever one you want to do. If you want to complete the square, I'll do it off to the side. But the quadratic formula is negative b, which in this case is negative 4. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So I get negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 1 all over 2 times 1. So that equals 4 plus or minus I wrote this wrong, didn't I? This is a minus 1. I'm so sorry, y'all. I am so tired right now. Okay, so this is 16 and then plus 4, so this will be 20 all over 2. And the square root of 20 we know is the square root of 4 times the square root of 5, right? This is going to be 2 square roots of 5 divided by 2. And then we can split that. And then it simplifies to 2 plus or minus the square root of 5. And so those are our 3 roots. Since we have a cubic, we're going to have 3 roots. Or if we don't have 3, we at least have something with a multiplicity of something. So the quadratic formula says that. So we have this one, and then we have these 2 roots. So my zeros are going to be negative 3, going to be 2 plus the square root of 5, and then 2 minus the square root of 5. Okay, just keep swimming. That's what Dory said. Just keep swimming. Okay. Ooh, 24. That one's got a lot, right? So sometimes we might want to narrow it down just because we have so many here. Like we have positive negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, positive negative 8, positive negative 12, positive negative 24. Okay? So since we have so many, we need to narrow it down. Okay? And then what we're going to do is we're going to go ahead and graph it so that way we can decide which one it is. So x to the power of 4 minus 6x squared minus 8x plus 24 and if we graph it, I'm going to draw the graph over here. Because if I graph it, I see that it turns and touches right there at 2, right? That's what ends up happening. So this has an even multiplicity here. At 2, but that means that 2 is going to be a 0. So let's go ahead and divide it. We got 1, then 0, then negative 6, negative 8, and then 24. And sure enough, we get 0. Okay, and so the reason why I'm mentioning this even multiplicity, because this means that, so here I have x minus 2, and then I'm going to have x cubed plus 2x minus 2x minus 12. Okay, and so because of this, since it has an even multiplicity, I know that it bends, and so that means on this, that means this is going to happen an even amount of times. So that means that it's going to at least happen 1 more time, if not 2 more times. So I'm going to have a 2, and I'm going to carry down that, it's a cubic now that I have. And this comes down 1, 2, 4, 8, 6, and 12, which gives me 0. And so now I'm left with x minus 2 squared, x cubed, plus 2x squared, minus 2x minus 12. Forgot a squared up here. Just kidding. X minus 2 squared, and then I'm going to have this, which is x squared plus 4x plus 6. Okay, again, this is not factorable. So just because you can use the quadratic formula, but just for good measure, we're going to go ahead and complete the square here. We're going to leave this equals 0. I'm going to move that to the other side and leave a blank. When I leave a blank, I take this and I take half of it, which is 2 squared, which is 4, right? That's going to be x plus 2 squared equals negative 2. We take the square root, so we have x plus 2 equals plus or minus the square root of negative 2. But we know that changes, doesn't it? That changes to plus or minus I square root of 2. And then that comes to the other side. So it's negative 2 plus or minus I square root of 2. Okay, so we have 3 roots. 2 of them are imaginary, the other one's real. But the zeros are going to be 2. Remember, 2 has a multiplicity of 2. Negative 2 plus I square roots of 2. And then negative 2 minus I square roots of 2. Okay? All right. So we have this thing called linear factorization, and so we need to also be able to take the zeros and write them as a linear factorization. So looking at that with example 5, we had negative 2 plus I square roots of 2. And then we had negative 2 minus I square roots of 2. And then we had x minus 2, x minus 2. In this case, there is not a coefficient because I knew it was 1. But sometimes there is a coefficient that factors out. And so we need to see that. So it says find a 4th degree polynomial function f of x with real coefficients that has negative 2, 2, and I as zeros, such that f of 3 equals negative 150. Okay, so here, in this one, we know that this one has roots that occur at plus, since it's positive I, it's also going to be also negative I. Okay. So if I were to write this as like some linear factorization, it would be an times x plus 2, which would be this one, x minus 2, which would be this one, and then we have these two, which is x minus I, and then x plus I. But this one we know we can rewrite differently, okay? Because I know I can FOIL this. N equals this, but then it's going to be x squared plus 1, because this is going to be x times x, which is x squared, and we have negative ix, positive ix, and then negative I. Another way to think about this is if you have I as a root, x equals the square root of negative 1, and so that means x squared equals negative 1 when I square both sides. And if I move that to the other side, the original factor that I had was this, okay? So conjugates always happen like that. Square roots will always happen like that too, okay? Because you end up squaring, creating 2 of them. Okay, well, that's my f of x. And so in this case, I know f of 3 equals a sub n of 3 plus 2, 3 minus 2, 3 squared plus 1, which actually in this case is negative 150. 5, 1, and then 10. 50 times an, which in this case gives me a sub n equaling negative 3. So my polynomial function is going to be negative 3, x plus 2, x minus 2, and then I have x squared plus 1. Or I could say x plus I, x minus I. And they did in the textbook boil this out. I don't know if your homework is going to ask you to do that. But here it is if they do. Okay. And that would be just by taking turns. Like you would get x squared minus 4, and then you'd have that, and then you'd have to take turns foiling this out, and then multiplying the 3 after. Okay. Last page of notes. Almost done. This 30-minute video. Okay, so we have Descartes' rule of signs, which says that the positive number of zeros is either the same as the number of sign changes of f of x, or less than the number of sign changes by a positive even integer. It means if my sign changes 4 times, it's either 4 or 2 or 0, positive roots. Okay, if I have negative real zeros, it's either going to be the same number of sign changes of f of negative x, or less than the number of sign changes by a positive even integer. So if I have 3, that means there's 3 positive roots, or 1 positive real roots. Okay? So if I have no positive sign changes, which means no positive real zeros. Okay? But if I plug in negative x, this would be negative x cubed plus 2x squared minus 5x plus 4. And if we look, that has 1, 2, 3 sign changes. Okay, so that means that there are either 3 or 1 negative real root. And actually, just so we can get on it, this would be positive or negative 4, positive negative 2, positive negative 1. So like here are my roots. But we already know that there are 0 positive real roots, so it's either going to be negative 4, negative 2, negative 1. And hopefully this helps you see how you can eliminate some choices. And just for the sake of time, we're going to show you that it's negative 1. So we have 1, 2, 5, 4. Okay. And so then we get x squared plus 1x plus 4, which in this case will not give me a real root. Remember, we've also checked the discriminant here, so this is b squared minus 4ac. And if this is negative, which I think in this case it is, yep, sure enough, 1 minus 16 is certainly negative. That means it's going to have 2 imaginary roots. So 2 imaginary roots. But anyway, the question was asking the roots. So hopefully this video helped you with 3-4, and I'll be back tomorrow to help you with your homework. Okay? All right, thanks guys.